Welcome back to session 23. This is part 2 on failure criteria. In the last session, or the last portion of the session, we discussed safety factors. In this part, we're going to discuss the Mohr criterion for brittle materials. And as I mentioned just briefly, this is essentially an extension of the maximum normal stress theory, but accounting for the fact that ultimate compressive strengths are generally higher than ultimate tensile strengths in brittle materials. Now, let's just go back a little bit and review the ideas associated with theories of failure. One, there's not a single unifying theory for failure, and these models do not account for all factors: temperature, rate of loading, corrosion, processing, even variation in the type of mechanical loading that you might expect. And we've discussed previously the maximum normal stress criterion for brittle materials, and we've also discussed how we need to use these with caution because there is high variability in the failure of these brittle materials. The failure can be sudden or catastrophic without much warning, and essentially you're dealing with shattering or the breaking of glass. The ductile materials, okay, are a little more forgiving and tend to be a little less variable in how they fail. The one that we've discussed up to this point is the maximum shear stress, or Tresca criterion, and in the third portion, or the third part of today's session, we will discuss the maximum distortion energy criterion, also known by the name Henke, or von Mises, or Huber, or Maxwell. A number of people were involved in the thoughts behind the maximum distortion energy, and so their names are associated with them. Typically, when you're dealing with simulation packages, though, you're going to see von Mises. So we discuss how there's generally less variability, and we have more of a gradual failure, and we can see that these materials may have some type of necking or elongation behavior at break. Failure in brittle materials, again, can be sudden. There may not be apparent yielding. It can just catastrophically go. And we have also discussed how the plane of fracture is orthogonal or normal to the stress. So here we were pulling the material apart and it breaks, and the plane of fracture is orthogonal to the internal stress, the uniaxial load, and we consider what is happening with a equivalent sigma max or an equivalent maximum normal stress, and we can say that that is why it's going to fail. So nothing's changing in terms of our thought process for brittle materials here. And we also discussed how we can, and we showed an example where we twisted a piece of chalk and we're able to get the kind of helical profile for the break. And if you take a piece of chalk, I don't think I have one now. Oh, I think I don't know. I guess I returned it. But if you take a piece of chalk and you also just break it like that, you're putting bending stress, not uniform bending stress across it, but bending stress across that thickness profile. At the neutral axis, the bending stress would be 0. But anyway, you can also get a very nice solid break because the fracture plane is orthogonal to the normal stress. Okay? And so this slide is from session 22. And if you like, you can go back and kind of review what we discussed in a little bit more detail, a little bit more slowly in terms of how we think about fracture happening orthogonal to this normal stress being applied. Okay, so this was under pure shear, and now we're saying, look, there are going to be normal stresses when we rotate 45 degrees, and we are now at the point where we're saying there's going to be a fracture line. It's orthogonal to that normal stress. And since the stress is, or the ultimate tensile strength is lower than the compressive strength, we would expect fracture to happen when you have tension, more so than in compression, because this is also, right, if I were to draw a plane in the direction I'm moving the mouse, that's also orthogonal to a normal stress, but this is the compressive, the y prime direction is compressive, and we expect that you're going to have it happening more easily in the tensile direction. Okay, so and then if you twist, okay, then what you have is we're now specifying that there's going to be a fracture line, and we're going to see that fracture line coming here with the 45 degrees. Okay, so we discussed maximum normal stress criterion in the past, and that was essentially saying look at sigma 1, look at sigma 2, assume that the ultimate compressive strength and the ultimate tensile strength are the same, and if sigma 1 and sigma 2 or sigma 2 are greater than this ultimate strength, then we have failure. And we use Mohr circle to kind of look at the maximum or the field goal method of having the maximum normal stress between this minus sigma ultimate and this positive sigma ultimate. We also use the sigma 1, sigma 2 plot, okay, to plot out the region or the envelope in which we'd be safe, okay, and failure occurs outside the box. Now, we've also discussed that the compressive strength of brittle materials is typically higher than the yield strength. The maximum normal stress theory is not bad, but it's assuming that they were the same, that the ultimate tensile strength and the ultimate compressive strength were the same. So Mohr's failure criterion says, look, we know that many brittle materials have a different tensile compressive strength than did I say ultimate compressive? There's a difference between the ultimate tensile strength and the ultimate compressive strength. And let's look at how we might kind of account for this. And we're not going to go into this into too much detail, but you might, or others have looked at 3 ways of testing the material. One is looking at how it fails in tension, okay? And so we might draw a Mohr circle like that, right? And that's going kind of the positive direction on the stress strain curve. We can look at what happens in compression, okay? And when we do that, we have a larger Mohr circle, right? Typically, the brittle materials are able to handle more compressive loading, more compressive stress. Okay, so the Mohr circle ends up being bigger in that direction. And then we can look at what happens in torsion. And there's Mohr circle, and we're seeing that there's kind of this maximum shear stress, this ultimate shear stress associated with it. Then you do this kind of very interesting slick thing, and you say, okay, well, to not fail, we've got to be inside of these Mohr circles. Okay, that makes some sense, right? And because we're saying, okay, well, the maximum normal stress, right, is what we're concerned with, and so then we can actually kind of put this like tangent line to these circles right here and call this a failure envelope. We're not going to get into all the details there, but that's kind of the basic idea. And then we take a look at this failure envelope on a sigma 1, sigma 2 plot. Okay, and what we see is that in quadrant 1, we're pretty much looking exactly like we did for the maximum normal stress criterion, okay, on a sigma 1, sigma 2 plot. It's a box. And quadrant 3 is pretty much the same too, except we're just saying that, okay, the compressive strength is higher than the tensile strength, the ultimate tensile strength. So this box or this boundary goes a little bit more down to the left and it's bigger. So then the question is, how do we connect these two? Well, in the past, okay, what we did is we said we just made boxes for maximum normal stress theory. But here we're going to say it's a little bit more nuanced. We're going to be in this envelope, so we're going to be essentially not just using the ultimate um, normal stress for compression or the ultimate normal stress and tension. We're going to do something that's kind of connect this point to this point and this point to this point, and there's a little bit of a curve here. And so now this is the failure envelope, right? So it looks different. In some ways, it looks a little less forgiving than the maximum normal stress theory, and it looks something a little bit more similar to what you have with Tresca, okay, which is involving maximum shear stress. So it's kind of like this. And this curve, we're not going to describe equations to get this curve, but what we can do is come up with a linear approximation. Okay, so what we actually do is we draw a line from this point, right, which is going to be 0, comma, sigma ultimate compressive, right, to sigma ultimate tensile, comma, 0 over here. And this is going to be sigma ultimate compressive on this side here, and it's going to go until and that's comma 0 to go to 0, comma, sigma ultimate tensile. Does that make sense? So the failure envelope, okay, is going to have these bordering lines that we see here where we can describe them, okay, in terms of y equals mx plus b. We can describe them in terms of lines. And these are the equations that we can use for these lines. So what does this mean? That means that we want to be able to determine, right, whether or not you're inside that line or outside that line. And so that's like a greater than equal problem, and that's kind of like an algebra thing from what I understand, right? Where you do these inequalities and then you draw a line, you do these inequalities and say, okay, am I less or am I greater than, right? So we can evaluate like a sigma 1 and figure out, okay, what would the sigma 2 be if it's on that line, right? And if we're above or below, that determines whether or not we're within the envelope of failure. So here we have an example. We'll say we have a brittle material and we're going to have a depicted state of stress. In this case, we're going to do 2 sub-examples. And we want to know whether or not we anticipate failure according to Mohr criterion. So here's a similar one, uniaxial, 50 megapascals. Here's another one, pure shear, okay, 30 megapascals. And if we look at the Mohr circle for this case, right, it's familiar. It looks like sigma 1 equals 30 megapascals. All right, let's go over here though. We have sigma 1 is equal to 50 megapascals, sigma 2 is equal to 0, sigma 3 is equal to 0. If we plot out our sigma 1, sigma 2 plot for Mohr criterion, what we get is something that looks like this. And I'm just using linear approximations here. This is 0.100 over here. And where is our sigma 1? Where's our sigma 2? Well, sigma 1's 50. Sigma 2 and sigma 3 are both 0. So that's going to put me right here, right, in 50, comma 0. So we expect that we will not have failure because we're within the envelope. If we want to estimate what how safe we are, we could think of, well, a safety factor times sigma 1 has to be less than this sigma ultimate, okay, in tension, right? So this is maybe a little bit counterintuitive, but sometimes you can think of these safety factors as being multipliers. So how much do I have to multiply sigma 1 in order to get it to move to the right and be greater than or equal to my ultimate tensile compressive or ultimate tensile strength, okay? And I could be looking at multiplying sigma 1 and sigma 2, but sigma 2 is equal to 0, okay? So that's, I'm just going to stay on the horizontal axis. If we have a situation where we have a non-zero sigma 2, right, then we're multiplying both of them. And we're going to see, okay, which one of these ends up causing a problem first. So anyway, we have is, all right, I'm going to multiply sigma 1 by the safety factor until I get to the ultimate tensile strength. So the safety factor can be thought of as the ultimate tensile strength divided by my sigma 1, which is 50. So the safety factor ends up being 2. Now, let's go back to this example in the middle. We can say that we have our sigma 1 equals 30 megapascals, and we can also say that sigma 2 is equal to minus 30 megapascals. So where are we going to be on our sigma 1, sigma 2 plot? Well, we're going to be in quadrant 4, right? Because sigma 1 is 30 and sigma 2 is minus 30. So we're in this quadrant somewhere. So let's go ahead and kind of open this up a little bit. We can figure out what this line is, okay, based on the ultimate tensile compressive strength and the ultimate, wait, did I say ultimate? The ultimate compressive strength and the ultimate tensile strength, okay? And it's going to have a rise of the ultimate compressive strength, or the negative of it, I guess you could say. And it's running over 100, which is the ultimate tensile strength right there. And it starts as a y-intercept of minus 150. So if we look at the value, the sigma 2 line, when we plug in our sigma 1 of 30 megapascals, that's going to give us a value on this line of minus 105 megapascals. So that's the point right there, right? All we're doing is we're figuring out where we are on the line. And now if we compare that to the 30 comma minus 30, right, what do we see? We see that we are in the box or in the envelope, right? So we don't expect to have failure. So we expect to be safe. How would we calculate a safety factor though? How do we do this? Well, we multiply the safety factor times sigma 1 such that we go outside of the envelope. So here, okay, we have the line that's given by Mohr criterion. This is the linear approximation. And we have our point where we have our operation. And if we multiply our sigma 1, that means we're also multiplying our sigma 2. So what we can actually do is think of, well, this is 30 comma minus 30. This is a line. This line has a name. It's called the pure shear line, actually. Okay, and we'll show a little bit more on this in the future. This line, right, is where we're going to be moving as we scale our sigma 1. Okay, and when we cross that line, that is when we're no longer going to be safe. So how much can we multiply 30 comma minus 30 until we go past the line? Okay, and so here we go. Where do the green and this purplish line intersect? Well, we know this purplish line is sigma 2 equals minus negative sigma 1. We know that the green line is given by Mohr criterion. We already figured that out. And so we substitute in sigma 2 goes minus sigma 1 over here. And then we can solve for sigma 1. So this is where it intersects. Sigma 1 equals 60. All right? So what is our safety factor? Once again, our safety factor is going to be equal to 2. Right? We can multiply, we can do our sigma 1 intercept divided by our sigma 1, which is 30. So this is 60 divided by 30 is equal to 2. Okay. So the question here for this portion of session 23 is, given this state of stress, which actually we've seen before, and please note that in session 22, I made a boo-boo, okay, or I made a mistake. So it's an opportunity to go back and look at the slides which I've corrected. Okay, there was an issue when I calculated the radius previously, and I only found that out this morning as I was running through, well, problems with this element, and things weren't working out. So anyway, so go back if you want to figure out how to calculate the maximum normal stress appropriately using Mohr circle. It's a minor mistake, but nonetheless, it does make, actually, it's a minor mistake that makes quite a bit of difference in the numbers. So the question is, will the brittle material, okay, with this state of stress fail according to the Mohr criterion if the ultimate compressive strength is 115 megapascals and the ultimate tensile strength is 100 megapascals, right? And that concludes part 2.